Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. We are on chapter 11, part 3. So in this section, we're going to be talking more about the correlation coefficient, otherwise denoted with the letter R. Okay, the correlation is going to measure the strength and direction of the linear relationship between X and Y, right? When we're just talking about two variables, we just have one explanatory variable and one response variable. Okay, so if R is equal to 0 or somewhat close to 0, that doesn't mean there's no relationship. It just means there's not a linear relationship. Otherwise, if R is equal to 1 or -1, it's a perfect linear relationship. In the case where R equals 1, you have points that all lie exactly on a line with a positive slope. Okay, this would be R equals 1. And if you have a correlation of -1, all the points lie exactly on a line, right? But now you have a negative slope, so R equals -1. Okay, so if your slope is positive, then R is positive, right? So if I have a data set that is scattered, I'm going to fit the best fitting line to that data set. And when I do that, it's going to go through there. So whenever I have a positive slope, that means that my correlation is going to be positive. So if beta hat 1 is greater than 0, then the correlation is also greater than 0. And the opposite is true as well. If beta hat 1 is less than 0, then the correlation is also going to be less than 0. Okay, so if the slope is positive, R is positive, and we're going to say as X increases, Y increases on average. And you have three choices: a strong positive linear relationship between X and Y, a moderate positive linear relationship between X and Y, or a weak positive linear relationship between X and Y. So at the strong side, R is going to be close to 1. And on the weak side, R is close to 0, right? So as our strength decreases, we get closer and closer to 0. If the slope's negative, then R is also negative. So as X increases, Y decreases on average, right? And you could either say there's a strong negative linear relationship between X and Y, there's a moderate negative linear relationship between X and Y, there's a weak negative linear relationship between X and Y. So in this case, R equals -1 when it's strong, and it's very close to 0 when it's weak. And we approach 0 as the strength decreases, right? Okay, one thing to note is I have a bunch of parentheses on this slide, and that is wherever you're going to change it to the context of the problem. So if we were studying high school GPA and SAT scores, then X you would use as high school GPA and Y you would use as SAT scores. So then you would just change those X's and Y's appropriately so it reads in context of the problem. If you'd like an equation for the correlation, here it is. Your correlation, remember, is always going to match the positive or negativity or the sign of beta hat 1. And then you can take the square root of R squared. Another equation you could use is to say that that's equal to SXY divided by the square root of SXX times SYY. Remember, that's your sum of your X deviations times your Y deviations for SXY. And for SXX, that's sum of your X deviations squared. And for SYY, that's your sum of your Y deviations squared. So moving on, we are going to talk about the correlation coefficient one more time and give you an example of a graph. Remember that in general, the correlation is either negative or positive. The values range from -1 all the way up to +1. Okay, it can be strong, moderate, or weak. And these are really just rules of thumb more than exact cutoffs. But in general, this holds true, is that you're at -1, very close to being strong, and you can see that there's a negative relationship for this -0.1. For the -0.7, you still have a negative slope, but the points are starting to spread out. For r equals -0.4, there's almost this like departure from the linearity on the left side. And then r equals 0, the points look like way more random and like a blob, but maybe I drew the best fitting line there. But maybe if you saw these other points, you wouldn't know if you needed to draw it there, or maybe, you know, it's hard to tell without doing the math of the exact line that's going through that. But once we get up to 0.3, it's clear that these are going in a positive relationship, but they're very spread out. Then r equals 0.8, we can see those points are getting tighter and tighter, and r equals 1, they all fall on a line. So you go from those negative slopes to those positive slopes. So the correlation can help you know how tight are those points fitting around that line, right? Are they exactly on the line, or are they more spread out? And it's telling you the strength as well as the direction of the linear relationship. So I hope you learned something in the video today, and I'll see you next time.